Hello, my name is Marsha and my final thesis presentation is on the dosimetric evaluation of an intraoperative radiotherapy system, a measurement-based and Monte Carlo modelling investigation. Before we start, I'd like to acknowledge my supervisors, David, Pedgman, Gabor and Martin. Without their help, this thesis wouldn't have been possible. Quick presentation overview. I'll be talking about the introduction and background, moving on to literature review, materials and method, results and discussion, and finally the conclusion and future work. The introduction. There are three main ways to treat cancer: surgery, radiotherapy, and chemotherapy. Intraoperative radiotherapy combines the first two. Imagine you've got a patient who has had the bulk of their tumour taken out in surgery. There may be some tumour cells that can't be seen to the eye. You can fit in what's called the Intrabeam probe and it'll kill off any remaining cancer cells. IORT typically involves a high radiation dose of about 10 to 20 grays. It's delivered in a single fraction of 10 to 30 minutes. There are three different types, one using high energy electrons, one using high dose rate radioactive sources, and one using low energy X-rays, which is what we'll be talking about today. You might ask why you don't just irradiate the patient with an external beam after surgery. Well, in many cases, to achieve sufficient local control, the radiation doses to kill the cancer must exceed the tolerance dose of surrounding healthy tissues. This is where IORT comes in. It increases local control while minimising normal tissue complications. It's normally used for breast cancer, pancreatic cancer, or spinal metastases, but most often for early stage breast cancer requiring lumpectomy. What's really interesting about IORT treatment is that for patients undergoing breast conservation surgery, the presence of a wound fluid after surgery stimulates proliferation, migration, and invasion of cancer cells. However, with targeted intraoperative radiotherapy, this negative effect of wound fluids is almost completely gone. Other benefits include the reduction of post-surgical treatment times for patients from 6.5 weeks down to 3 to 5, or it can eliminate post-surgical treatment entirely. Patients can benefit from a complete treatment while being sedated, and there's evidence to show that it increases overall survival time and quality of life in patients. This is the Zeiss Intrabeam, which this thesis is based on. As you can see, there's a cathode gun, which produces electrons that are accelerated down the probe, eventually striking a goal target to produce X-rays. The source has a maximum energy of 50 kV, and the X-rays emitted are approximately isotropic and they're very quickly attenuated. Of course, you can shield the intrabeam in any particular direction if you so desire. This is a close-up view of the bare probe. As you can see, there's a beryllium window which is transparent to X-rays. The electrons will come down and strike this goal target and produce X-rays that are approximately isotropic in all directions. There are also different applicators that you can spit over the probe from 1.5 to 5 centimetres in 0.5 increments. It could be because the tumour bed is of different sizes, or it could be for different parts of the body, whether it be the breast or the liver, pancreas, etc. So moving on to Monte Carlo techniques, they attempt to model real-life systems. They exploit randomness and the central limit theorem, and they sample representative electrons and photons and transport it according to average interaction probabilities. What that means is that for each particle, it will travel some distance, interact with the medium, either deposit energy or eject a secondary electron, or both, and it will be scattered with a new energy in a new direction. And this continues for each particle until it leaves the volume of interest or its energy falls below the defined threshold. If that happens, it will just get absorbed where it is, and that's deposited as dose. Take note that the Monte Carlo error is proportional to 1 on the square root of the number of histories. The more histories you use, the smaller your error. So there are several toolkits suitable for Monte Carlo simulation in radiation dosimetry applications. GEONT4, MCNP, Penelope, and EGGS are the most common ones. This thesis uses EGGS NRC, and it simulates photons, electrons, and positrons, with kinetic energy range of 1 keV to 10 keV. The media must be homogeneous, but it can be elements, compounds, or mixtures. EGS is capable of simulating complex geometries and particle sources. Moving on to a quick literature review. This is a summary table of key articles. As you can see, some use spherical applicators, some use film, ionization chambers, TLD or solid state detectors for dosimetric measurements. And other articles perform a Monte Carlo simulation of the Intrabeam using various different Monte Carlo toolkits. But the main takeaway is that of the articles that use film, not many of them perform film measurements in water. Eaton and Duck uses film in water, but they use scissors and tape, which would have introduced some sort of uncertainty. Moriarty uses film in a PVC sheet, which is placed on the surface of the water, whereas we are more interested in immersing the film directly in water. Watson et al. Was quite impressive in that they 3D printed a film holder to suspend the film in water. However, they only investigated the bare probe, and we'd like to investigate the probe and applicators. In terms of Monte Carlo, only 2 articles use all 3 coatings in their Monte Carlo design. I'll talk a bit more about this later, but it has an effect on the results. This is just a summary of a couple of articles and their results. On the left, Moriarty used Monte Carlo and film, and on the right, Shamsabadi used Monte Carlo and ionization chamber measurements. So just keep in mind the kind of shapes and plots that we're expecting from this thesis. A quick overview of research aims. So this thesis aimed to evaluate dose from the Intrabeam. So first we obtained the dose distribution data from Monte Carlo for the bare probe and all applicators. We wanted to verify this data with measurements by ionization chambers, and if that all went well, we wanted to compare further Monte Carlo simulations with film results. Materials and method. This is the Monte Carlo design for the bare probe. As you can see, it has 3 coatings, so this image is not to scale. Nickel oxide, nickel, and chromium nitride on the outside of the probe. They're each 2.5 micrometers thick, and the gold target here is 1 micrometers thick. Some articles use a thickness of 0.5, but in here we've used 1 micrometer thick according to Monco et al. The Monte Carlo source is an electron source with a Gaussian energy distribution with mean 50 keV and full width half maximum 5 keV in accordance with vendor specification. According to Clausen et al., the electrons strike the target with 2 rings, one with 0.6 to 0.7 millimeters in radii with a weighting of 1.05 and a secondary ring with 0.7 to 0.8 millimeters in radii with 1.55 weighting. Clausen et al. Found that all the other rings were negligible. So this is how I've modelled the electron source on Monte Carlo. For the applicators, things were a little bit more complicated. The manufacturer doesn't provide any information about the dimensions. So we had to take an X-ray of each applicator, perform edge detection on image J, and then extract those dimensions manually to produce what you see on the right here, which is the Monte Carlo design. You can see that there's a blue aluminium filter present in this diagram. This filter is only present for the smaller applicators, less than 3 centimeters in diameter. For Monte Carlo simulations, the threshold energies for electron production were from 515 keV to 700 keV. So this includes the kinetic energy and the rest mass energy of the electron. For photon production, the threshold was 1 to 200 keV. And if electrons fall below 513, and if photons fall below 1 keV, they're absorbed into the medium. The simulations are run in 2 steps. First, we obtain a phase space file of 10 times 10 to the power 9, 8 times 10 to the power 9 histories. So this was scored with the Bayer probe, and it scored every single X-ray exiting the probe. And we used this phase space file for further simulations of the applicators, and this saved a lot of time. So for our physical measurements, take note that the ionization chamber measurements were made in the Z-axis and the film measurements were made in the XY plane. And this is because of the setup of the Zeiss water tank. As you can see at the bottom here is where you place your ionization chamber. So you can only measure the PDD in this Z direction. And for the film measurements, we had to measure it in the XY plane because this ionization chamber holder was in the way. So the water tank we used was the one provided by Zeiss, the Zeiss Intrabeam water phantom. The ionization chamber was a soft X-ray parallel plate chamber, and the electrometer I used was the PTW Unidos E. So we made measurements for each probe, for each applicator and the probe. About 7 depths were measured, and there were 3 readings per depth. Just for completion, this is the Zeiss Dosimetry protocol that was used to determine dose rate in water from the chamber reading. I won't spend too much time here, but it's here if you'd like to look at it. For estimating the uncertainty from chamber measurements, we use this formula. So it includes the standard deviation from the 3 chamber readings, the relative uncertainty due to chamber positioning, the relative uncertainty of the product of these 3 factors, which are given by Zeiss, and the uncertainty from measuring pressure and temperature. As you can see, for all individual measurements, the uncertainty was quite low, less than 2.32%. So in terms of comparing ionization chamber and Monte Carlo PDDs, we had to fit a curve to the Monte Carlo data so that we could get the same depths as the chamber readings. This equation was used. The x squared is due, the 1 on x squared is due to the inverse square law, and the decaying exponential represents the attenuation. However, for the Bayer probe, we used a slightly different formula, only because it gave a better fit. To get RMSD values, we took the ionization chamber reading for each depth and subtracted the Monte Carlo result at that same depth. Moving on to film measurements, 2 things needed to be done first. We needed to 3D print a film holder to hold the film in water, and we needed to laser cut some film designs. So this is the film holder here. You can see that there's a little slot for the film to fit into and legs of 8 centimeters long. So this was printed using PLA with 93% infill, which is water equivalent. 2 types of film sizes were printed. One was rectangular. This was used to measure probe and applicators. And the second was square, just for the probe only. These were the rectangular film sizes. We irradiated several applicators and the probe, and they were prescribed a 2-gray dose at 10 millimeter from the applicator surface or the probe isocenter. And these were the square film irradiations. The Bayer probe was given a range of doses at 10 millimeters from the isocenter. So just take note that the film was placed right at the top of the hemisphere, just where it started. To analyze the film, we used the red channel in MATLAB. This is the most accurate. We obtained 5 pixel values, 5 rows of pixel values, averaged these, and then passed the median filter through it to reduce the noise. Moving on to results. These are the PDD measurements using Monte Carlo and ionization chambers. So the blue dots are from the chamber readings and the pink curve is from the Monte Carlo. Most of them have fairly good agreement with differences generally between 0 and -3 and 3%. The 1.5 centimeter applicator was the worst one with differences up to -9%. So remember that these measurements are made in that Z-axis at the top of the probe. So I'll just skip past these fairly quickly. Just take note of the differences. They're generally quite small. The plot on the right is all of the Monte Carlo plots for the PDDs. So there was pretty good agreement with the Monte Carlo and chamber readings, with most differences less than 3%, except for the 1.5 centimeter applicator. But for some of the plots, you could see a clear shift between the chamber PDD and the Monte Carlo PDD. So we just shifted things slightly left to right, and it made a big difference to results. So these are represented as uncertainties on the previous plots. So why might there have been a systematic shift? It could be either due to the chamber positioning or the probe positioning. Most likely the first, because the latter is quite small. Monte Carlo uncertainties were larger, up to 6.48%, with coverage factor of 3. To improve these, we could introduce more histories and run simulations again. We could also reduce the Monte Carlo voxel sizes so that a fitted curve might not be needed at all. We could directly compare Monte Carlo and film results at the same depth. To improve the ionization chamber measurements, we could use more data points, as this would improve accuracy. So in summary, you can see that the bare probe has the sharpest dose fall off, and the smaller applicators have a sharper gradient as well. The main reason is due to the inverse square law, and a minor contribution is due to attenuation. The implication of this is that smaller applicators can allow for greater skin sparing and shorter treatment times if the smaller applicators fit the tumour bed. These are the PDD results for film. The orange line is the Monte Carlo fitted curve, and the green dots are the film measurements. As you can see, there's some discrepancy, especially in that right graph, but most of them are pretty good. It's quite noisy, even though we passed a median filter through it. So in summary, there is fairly good agreement, especially at further distances, but that steep initial dose fall off means that small shifts result in big differences, up to 10%. To improve these results, we could calibrate the film and we could investigate whether there is some source of uncertainty for the first few millimeters, whether it be water damage or heat damage from the laser. Comparing the Monte Carlo and ionization chamber results, you can see that the profiles are generally the same shape, which is expected because the manufacturer claims that the dose should be fairly isotropic. This is the energy spectrum that we obtained. The black is from this thesis and the blue line is from another article which uses the same coatings as we did. You can see that the coatings make a difference because when we compare it to a different article that didn't use the nickel coatings, there is a clear shift in the spectrum. So these two peaks at the beginning are from chromium. These middle ones are from nickel and the higher ones are from gold. This is the energy spectrum for all the other applicators. They attenuate some of the lower energy photons from the bare probe. So you're just left with a curve like this. And you can see that the presence of the aluminium filter in the smaller applicators has shifted the peaks to the right. So comparing the mean photon energies from this thesis, the Bear probe had a mean energy of 21.19 keV, which was slightly higher than what the manufacturer said it would be. And it was also higher compared to other literature. And the same deal is with the applicators. Our average energy is also slightly higher than elsewhere. Reasons for this could be differences in the probe geometry, like I mentioned earlier with the 3 coatings. It could also be due to the gold thickness. Here we use 1 micrometers, whereas these 2 articles use 0.5. And it could be differences in the applicator geometry design because it's difficult to know the exact dimensions. These are the Monte Carlo Isodose curves at 10 millimeters from the Z equals 0 axis. So the main takeaway here is that you can see that the dose spreads further for larger applicators as expected, and you can see that the dose distribution is about the same in each direction, which it should be. These are the same curves for the film, except in the x-axis, and you can see again that the dose spreads further for larger applicators. What's very interesting is for the Bear probe in this XY plane at Z equals 0. So just before the goal target begins, you can see a sort of build-up of dose. The left one is from Monte Carlo. It looks a bit pixelated because of the voxel sizes. But yeah, you can see that the dose builds up to the yellow before it decreases again. And the same thing can be observed in film. The dose builds up and then decreases yet again. Just take note that that yellow region in the center is actually the hole cut out from film. So to conclude, the results obtained from this thesis provide greater insight into the dose distribution of the Intrabeam at Sir Charles Gairdner Hospital. This is important because each Intrabeam is slightly different due to manufacturing differences. These results can be used to treat patients more accurately. The Monte Carlo phase space file that we obtained can also act as the virtual source for any future research on the Intrabeam. This would save a lot of time. For possible future work, we could make more measurements with film, but this time in solid water, and compare results. Because we could also make measurements with TLDs. This would be quite interesting to compare. It would be a good idea also to further investigate the feasibility of using film directly in water. We could also try to modulate the intensity of the dose delivery by printing 3D applicators with non-uniform densities and asymmetric shapes. For patients that might need greater dose in certain regions, but not so much on the other side. Special thank you again to my supervisors, Pejman, David, Gabor and Martin. Thank you to the Department of Radiation Oncology at Sir Charles Gairdner Hospital for funding this research and providing the equipment. Thank you to Mashid, Andrew, Leslie, Riley, Marcus, Warwick, Tanisha, Rachel, Hannon and Matthew for help with imaging, Monte Carlo, 3D printing, laser cutting and taking photos. And thank you to Cancer Council Western Australia for the research grant. Thank you for listening. Are there any questions?
Thanks very much. It's great. Brilliant. Excellent work. Any questions from Marsha? No question. It's great. Good one, Marsha.
Nice work, Marsha. It's quite very good work. So just like a question for you, if you want to commission this device and you've been asking to validate the PDDs, would you use Monte Carlo's method to validate the PDDs or would you measure it?
I think I would measure it, only because each Intrabeam device can be slightly different. And if you just nudge the probe slightly, you could get different results. So if I were to treat patients using that device, I think I'd at least check that the results from measurements agree with my Monte Carlo before trusting the Monte Carlo. Does that make sense?
Thanks. Yeah, good.
I just got a question as well. Very good work. When you said you did the film in the XY plane and then the ion chamber in the Z plane, did you validate the isotropy of the Intrabeam before you did that, or did you just assume that it was isotropic?
No, we didn't really investigate the isotropy that much. Yeah. That could be something for future work to qualify, to quantify the isotropy.
Is any literature available? Have you went through? Have you noticed it during your literature review?
Sorry, any pictures of?
No, I'm saying in the literature review, have you have you found anything someone has done about the isotropy investigation?
Yes, I did come across one. I don't have a photo of it, but it's a spider plot.
Oh, okay.
Yeah.
Spider. Oh, yeah. Okay. Yeah. Fair enough. It should be look like the spider plot because it's only in a one dimension, isn't it?
Yes. It would be in one plane.
The other option is gel dosimetry. We can insert the.
That's a good point. Yeah. That could be the brilliant idea.
Previously, I gave Marsha all the commissioning measurements, and in there we measured isotropy in two main planes with Gottfried's plastic phantom. But as I mentioned earlier, that we have always problem to measure the isotropy because the manufacturer stated plus minus, I think 5%, and sometimes we measured around 10% or even greater. So we tried different methods. None of them was working, and this is what is inspired Gottfried to design this isotropic plastic phantom, and it needs a lot of tweaking and nudging to make it work, and that is we use it as our standard. So this is what we use, but again I would say within 5%. But I think Monte Carlo and with the film measurements are below 5%. So we can't validate, at least just said we are good within 5%, but I think Monte Carlo and the actual film measurements could give you better results. But previously we don't have the tools to validate it. And we had a lot of conversation with Zeiss about, what they state and what we measured and what was wrong in our measurements. And, this would the end result that Gottfried's plastic isotropy phantom.
Thanks, Gabor.
That's great.
Yeah, that's good. Thank you. Thank you, Gabor.
Any other questions? All good? No questions, no comments? That's great. Thanks very much, Marsha. That was a great presentation. Well done.
Thank you.
Excellent. Good. And Roderick, if you can please stop recording, that would be great.